Okay, good afternoon, everyone. Welcome to the IMS Grace Wahba Award and Lecture Session. My name is Jing Lei. I'm a faculty member at Carnegie Mellon. Today, I'm very much my great pleasure and honor to chair this very special session. So to begin with, let me introduce Grace Wahba, which this session is named after. Grace Wahba, one of the outstanding statisticians of our age, is currently Emerita I.J. Schoenberg Hilldale Professor of Statistics at the University of Wisconsin-Madison. She has transformed the fields of mathematical statistics and applied statistics. She has made fundamental contributions to mathematical and applied statistics optimization and machine learning. So for a few important keywords we are all familiar with, including smoothing splines, reproducing kernel Hilbert spaces, the representer theorem, and generalized cross-validation. These theory and methods are now field standards and have profoundly impacted practical applications in science, engineering, and medicine. The IMS Grace Wahba Award and Lecture is to honor Grace Wahba's monumental contributions to statistics and science. These include her pioneering and influential work in mathematical statistics, machine learning and optimization, broad and career-long interdisciplinary collaborations that have had significant impact in epidemiology, bioinformatics, and climate sciences, and outstanding mentoring as an educator. So this year, the awardee, the recipient of the Grace Wahba Award is Professor Richard Samworth. Professor Richard Samworth obtained his PhD in statistics from the University of Cambridge in 2004 and has remained in Cambridge since, becoming a full professor in 2013 and the professor of statistical science in 2017. His main research interests are in nonparametric and high-dimensional statistics. He has developed methods and a theory for shape-constraint inference, missing data, subgroup selection, data perturbation techniques, change point estimation, variable selection, and independence testing. So Richard has earned a long list of honors and achievements. Here I will just highlight a few. He received the COPS President's Award in 2018, was elected as a Fellow of the Royal Society in 2021, and was awarded the David Cox Medal for Statistics and the Royal Statistical Society Guy Medal in Silver in 2025. He served as co-editor of the Annals of Statistics from 2019 to 2021 and will become IMS President-elect after this JSM. So today, Professor Samworth will talk about nonparametric inference under shape constraints, past, present, and future. Now here I will present the medal of the award.
So thank you, Jing, for that extremely kind introduction. I'm extremely grateful to the IMS, the Committee on Special Lectures, but also my nominators for putting me forward for this lecture. It's really an enormous honor and a pleasure to be here. Okay, so this is going to be a talk that's going to come in two parts. The first part will be a kind of whistle-stop tour through kind of 60 years of shape constraints, 70 years of shape constraints, with a particular focus on sort of core problems like density estimation. I could have put regression into that category, but I don't think I'll have time to say so much about that. And then the second part of the talk will be a kind of very ongoing development that I'm working on related to how we should do linear regression, or that's we could think of it like that, which you can regard as a kind of application of some of these techniques, but takes us in a slightly different direction. So there'll be a sort of pause halfway through. Okay, I thought I'd start also by saying a few words about Grace. Jing's already given a great introduction to her outstanding contributions. Grace has been a really trailblazing figure in statistics, machine learning for many, many years. I've been fortunate enough to meet her on a few occasions. I even went to her group meeting once when I was in Madison. She's a really remarkable figure and a pioneer of our field, and I'm delighted to be able to give the lecture in her name. Okay, so this is the sort of beginning of part one. I want to start really from the very basics, and so it'll be probably extremely simple to, I think, everyone here, but let's see how we go. So I want to start with one of the most basic problems we can think of in statistics. We like to ask, what distribution did my data come from? Fortunately, there are many ways in which we can ask this question because it keeps people like me gainfully employed. But one of the most fundamental is to say, how should we estimate the density that my data came from? So broadly, we can think of two different styles of approaches to tackling this problem. The first would be to propose a parametric model for our data. So in this example, I've drawn 200 observations from a gamma distribution. The gamma distribution is plotted in black there. And if we know that our data comes from this gamma distribution, then we can use a technique like maximum likelihood estimation to estimate the underlying parameters. And we can really do a remarkably good job even with this relatively small number of observations. Of course, there's the caveat, I run the statistics clinic in Cambridge, so once a fortnight, anyone in the university can come and get help with statistical problems. And I have to say, it's very rare that they come along and they say, I know my data came from a gamma distribution. Would you mind just estimating the parameters for me, right? And so what can go wrong? Well, maybe you thought these data came from a Gaussian distribution, and you apply the same ideas of maximum likelihood estimation, and what happens, this is the Gaussian distribution that you end up fitting, and it's a disaster, okay? So, of course, the difficulty is here that we're making this very strong restriction to a parametric model, and we lack the flexibility to fit complex data relationships. This has been known for a long time. So what happens if we try to extend the idea of maximum likelihood estimation from parametric models to non-parametric models? First, we need to make clear what we mean by the likelihood function. That's not so difficult to answer, actually, because when we talk about the likelihood of a particular parameter value, what we really mean is the likelihood of the density with that parameter value. So it's clear how we should define the notion of likelihood in this non-parametric context. We should define the likelihood of a density F to be the product of the density at the observation. So we're trying to make the density large on the observations. But we run into this trouble of what's known as the Dirac catastrophe. So our objective function is not bounded above. We can make it as large as we like because we can put approximations to delta masses, to point masses on each of the observations, and by making these spikes very tall and very thin, we can make this likelihood arbitrarily large, okay? And what's really going wrong here is that we don't really believe that all the mass of the true distribution is so tightly concentrated around the observations that we've seen. So that motivates the idea of smoothing. And one of the simplest ways in which we can do smoothing is via a method like kernel density estimation. So here's a very simple cartoon plot of a kernel density estimator with 5 observations in 1 dimension. So the idea is that we give mass 1 over n, in this case 1 over 5, to each one of our observations, and we kind of smooth it out a little bit. In this example, I've used what's called a Gaussian kernel to do this smoothing, and then we just get our overall density estimate by adding up the contributions from each of the individual terms. Okay, a very simple and intuitive estimator. And it can often work very well. The the kind of perhaps the primary issue here is that you need to choose the scaling of this Gaussian kernel, what's often called the bandwidth, very carefully. So here's an example where we're trying to estimate a mixture of Gaussians, mixture of two Gaussian densities. And on the right here, I've chosen the bandwidth to be too small. So that means we've got a kind of a tall and narrow kernel. We're not doing very much smoothing. And so we end up with a rather wiggly density estimate. This would have a high variance at each point, but a low bias. In the bottom right plot, we've rather over-smoothed the data, and this sort of washes out a feature of the density practice bimodality that we might be particularly interested in. And on the bottom left, we've got something like a kind of Goldilocks situation where it's not too large and not too small, and we're doing a pretty decent job of estimating this density. So kernel density estimation methods and variants of these types of methods are very popular as non-parametric density estimators, but there are still challenges both in terms of theory and in terms of how we should make these choices in practice, particularly in multidimensional situations. So this is where shape constraints and the first actor in our scene of Ulf Grenander is going to enter the scene. So Ulf Grenander was a Swedish statistician, and he made his sort of first contribution to this field in 1956. So here's the problem he thought about. We have some IID non-negative random variables, and I'm going to write curly G for the class of right continuous decreasing densities on the non-negative half-line. So Grenander proved that there exists a unique maximum likelihood estimator over this class. So there exists a unique maximum likelihood estimator over the class of right continuous decreasing densities on the non-negative half-line. So I've taken my likelihood and I've taken the logarithm and I've divided by n, but that doesn't change anything about the location of the maximizer. So this is a maximum likelihood estimator here. And actually he proved not just that this exists and is unique, but he was able to characterize it. So he proved that it can be thought of as the left derivative of the least concave majorant of the empirical distribution function. Okay, so this is a little bit of a mouthful. So let's see a picture of what's going on here. So this is a situation where we have 30 observations drawn from an exponential 1 density. And on the left plot, we're looking at things on the distribution function scale. And what's plotted in red is the empirical distribution function of this data. So these have got jumps of size 1 over 30, 1 over n at each of the observations. The true underlying distribution function is plotted in blue. That's the distribution function of the exponential 1 density. And what's done in black is I've drawn the least concave majorant of this empirical distribution function. And you can see the way that this is a piecewise affine function. Okay? And then what we have to do is take its right derivative. So because it's a piecewise affine function on the distribution function scale, when we take its right derivative, we're going to get a piecewise constant estimator. And this is what we're seeing on this right-hand plot. And at least to some extent, this is you can see that this is estimating this blue decreasing density. Okay, so we only have 30 observations. There's sort of a limit to how well we can hope to do this, but we hope that this would improve as the sample size gets larger, of course. Okay, so that's all very elegant. What can we say about how well the Grenander estimator estimates the underlying density? So here's a result, a very simple result that I think is very beautiful and says something about the performance of the Grenander estimator. It's actually thinking about it as a distribution function estimator rather than as a density estimator, but I'll say something more about density estimation in a moment. So I've got this blackboard bold Gn denoting the empirical distribution function, and then I've got a G hat n, which is our Grenander distribution function. So that is our least concave majorant of the empirical distribution function. And Marshall's lemma says that for any concave function G, the supremum norm distance between the Grenander distribution function and G is bounded above by the empirical distribution function difference in subnorm from G. Okay? So that's quite interesting. We think of the empirical distribution function as a very good estimator of the underlying distribution, and this is saying that the Grenander distribution function is at least as good as that. So the particularly interesting case here is where the data do come from a decreasing density on the non-negative half-line, because in that case, the distribution function is going to be a concave function. So if you think of this as being the true distribution function of the data when in a well-specified model, that's probably the primary case of interest here. So I'm going to be bold, even though it's early in the talk, and I'm going to prove this result. Okay? It's only a 4-line proof, and one of the lines is only a little bit of a line. So here's the first part of the proof. If I think about the function which maps x to g of x plus a constant, this infinity norm difference between the empirical distribution function and g, that is a concave function plus a constant, so it's still a concave function. And moreover, it majorizes the empirical distribution function because of its construction as g of x plus this supremum norm difference. But what I know is that the Grenander distribution function is the least concave majorant of the empirical distribution function. So what we know is that for each x, g hat n of x must be bounded above by this function here. Okay? So if I take the g of x over the other side, then I've got one of the bounds that I need here. To get the bound going the other way, I just have to notice that the Grenander distribution function does indeed majorize the empirical distribution function, so it's greater than or equal to this blackboard bold g hat n, and then that's at least g of x minus this constant value here. Okay? So that gives me the other bound. That's the proof, the whole proof, and nothing but the proof. Okay, so that's as a distribution function estimator. What can I say about it as a density estimator? Well, here's actually a much deeper result that I'm certainly not going to prove in front of you right now. That's due to Lucien Birget from 1987. So, okay, how are we going to think about how well the Grenander density estimate performs as a density estimator? First of all, we have to agree the rules of the game in terms of how we're going to measure the distance between our estimate and the truth. And in this case, Birget chose to measure distance in terms of a very natural notion of distance, the total variation distance between the densities, which I can think of as half the L1 distance between the corresponding densities. So one issue here is that when I have my estimator and I look at the total variation distance between the estimator and the truth, that's going to be a random quantity because it depends upon my random data. That's something that I can fix relatively easily because I can take the expectation of this total variation distance. That gives me a deterministic value. It might be called the risk of this estimator. But it also depends on which element of the underlying parameter space I drew my data from. Okay, so there's an underlying G0 here, and I want to think about the well-specified case where G0 is actually a decreasing density on the non-negative half-line. Actually, I'm going to make a stronger restriction than just saying that. I'm going to say insist that the density is bounded above by a quantity capital H, and it's supported on the interval from 0 to L. So by making H and L large, I kind of encompass a large subclass of these decreasing densities. But for instance, for no H and L would I capture the exponential 1 density that we saw before. So there is something of a restriction here. Well, if my risk function depends upon the G0, there are many things I might do. I might try to weight the different values of G0 in some way, perhaps via some sort of prior distribution. But perhaps a simpler thing to do is just take a look at the worst case over all G0s that I might look at. And here we're going to look at the worst case risk. So we take the supremum over all of these decreasing densities in this class curly GHL. That gives me a deterministic quantity, and I can think about trying to minimize that over all estimators. So then I can take the infimum over all estimators G hat n. So this is then a sort of mini-max type of result. It really should be called an infi-sup sort of result, but mini-max rolls off the tongue a little bit more easily. And what we're seeing is that this mini-max risk can be bounded above and below, and the ratio of the upper to the lower bound is a factor of 10. Okay? Now that may not seem very good to those of you who are used to more perhaps parametric models and well-specified parametric models, where we might even get sort of sharp results up to constants. But in non-parametric worlds, this is a success story for very often constants might be a lot bigger than that, or there might be logarithmic factors floating around. Here, the fact that this minimax risk is matching not just in the dependence on the sample size is the same on both sides of the bound, but also in terms of the parameters of the density or the parameters of the class. That is sort of good news for us here. The fact that the factor of 10 is a little bit artificial in the sense that the sample size condition has been chosen to guarantee that you have this factor of 10. If I imposed a stronger sample size condition, I could shrink that a little bit, or if I had a weaker sample size condition, it would get worse. So there are some interesting factors here. First of all, we notice that this minimax risk is scaling like n to the minus 1/3. Okay, I have to blow it up by n to the 1/3 to get this sort of non-degenerate terms on either side. That is sort of contrasted with the well-specified parametric models where we might hope typically for an n to the minus 1/2 rate of convergence. And this is reflecting the price we pay for working with our non-parametric model. We also see that the same dependence in terms of the underlying parameters of our class in the lower and upper bound. That's very nice. But as I say, we are making a restriction to the class. We're not covering all of these densities. And these types of results have been generalized in various different directions. You can go from decreasing densities to convex decreasing densities, and then the generalization of this is to K-monotone densities, and there's been some nice work in these directions. But actually, I want to focus on a slightly different direction, thinking about different shape constraints. So here's a very incomplete bibliography of some relatively recent work on different sorts of shape constraints. And the one that's going to be the focus for the rest of this talk in different ways is going to be the shape constraint of log concavity. Okay, so for those of you who are not familiar, a density is log concave if the logarithm of this density is concave. So one of the reasons that I particularly like this class, and perhaps why it's become rather a central object within the field of non-parametric inference and the shape constraints, is that the definition works equally well in d dimensions as it does in one dimension. When you're working with decreasing densities, it's not necessarily so easy to think of or to have a very natural generalization to the d-dimensional setting, but here it's very obvious. Another reason is that there are lots of examples that we can think of nice univariate densities that are log concave. Gaussian densities are log concave because their logarithm is a parabola. Okay? Logistic Gumbel densities, Weibel densities provided the shape parameters at least 1, gamma densities provided the shape parameters at least 1, so chi-squared densities in particular, if you've got at least 2 degrees of freedom, they'd be log concave. Beta AB densities provided the shape parameters at least 1, so uniform densities on an interval would be log concave. Maybe even more than these examples, which sort of indicating which is how you should think of the class of log concave densities, is that they're unimodal densities with exponentially decaying tails. But very attractive properties of this class are their stability properties. So the class is closed under marginalization. What do I mean by that? I mean that if you have a random vector x, which has got a log concave density, and you take a subset of its components, then that would have a log concave density. Okay? Likewise, the class is closed under conditioning and under convolution, and also under taking linear transformations. So one of the things that's very interesting about these 4 properties is that these 4 properties would be exactly shared by the class of Gaussian densities. Okay? So convolutions of Gaussian densities are Gaussian, and marginal densities of Gaussians are Gaussian. So for this reason, it's very natural to think of the class of log concave densities as an infinite dimensional generalization of the class of Gaussian densities. Okay, so the starting point for doing density estimation over the class of log concave densities was a theorem that I proved with Lutz Dumgen and Dominic Schumacher from nearly 15 years ago now. I need just a little bit of notation. I'll write curly PD for the set of all probability distributions on R to the D that have got a finite mean and that give mass less than 1 to every hyperplane. So that's saying that these are somehow genuinely d-dimensional distributions. They're not concentrated all on some sort of hyperplane. And the second piece of notation is I want to write curly FD for the set of upper semi-continuous log concave densities on R to the D. Don't worry too much about the upper semi-continuity. So actually all log concave densities would be continuous almost everywhere. It's only on the boundary of the support that they may have discontinuities, and I'm just saying fixing a particular version of the density. And the key result here, it may not be immediately apparent why this is key, but it does turn out to be key, is that there is a well-defined projection, and I'll write this as psi star, from this class curly PD to the class curly FD, and it's given by this map psi star P is the log concave density in my class curly FD that maximizes the integral of log f dp. Okay? So let's try and understand what's going on here. If I think of P, first of all, as an empirical distribution of some data, then certainly the sample mean of the data will be finite, so the first condition of belonging to curly PD will be satisfied. And then the second condition I could think of is just saying that the convex hull of my data is d-dimensional. Okay? But provided that's the case, we're saying here that there exists a unique log concave maximum likelihood estimator. So this is somehow a little bit of a holy grail because it's giving us a way of doing multi-dimensional non-parametric density estimation where you've got no tuning parameters to choose. Right? Choosing tuning parameters is kind of the bane of every non-parametric statistician's existence. So we don't have to do that here. So if this P had a density, let's call it F0, then essentially this psi star P is minimizing the Kullback-Leibler divergence from F to F0. Okay, so in that sense, you can think of this as kind of a projection onto this class curly FD, and you'll notice that I've drawn this class as a non-convex class. It is a non-convex class because, for instance, if I had a Gaussian distribution over here and a Gaussian distribution over here, and I took a 50-50 mixture of them, that's definitely not going to be unimodal, so it's not going to be within the log concave class. Okay? So I've drawn it as a sort of kidney bean shape. I could have drawn it as any other sort of non-convex shape. And that's what means it's not trivial to show that there exists this well-defined projection here, but there does. Good, okay, let's get a bit more of an intuition about this map. This map psi star, it turns out to be a really key, important map. So here's a couple of pictures of log concave projections. The first one, in the first one, the green density is a scaled T2 density. So T2 density has extremely heavy tails. It has a finite mean, so it belongs to the class curly PD, doesn't have a finite variance, for instance. And what we can prove in that case is that the log concave projection, the psi star, is the Laplace density. Okay? And you can see the way that even though the T2 density has very heavy tails, within this log concave class, it's doing a pretty decent job of approximating this distribution. Certainly, if you looked into the tails, the relative error would be a long way off if you went very far into the tails, because one is exponentially decaying and one is decaying like a slow polynomial. But at least on the scale that I'm plotting it, this looks pretty close. On the right, I've got a bivariate, a mixture of two Gaussian distributions, and what I can prove here is that the log concave projection exactly matches the truth up to some point, and then it's log linear, and then it exactly matches the truth in the right-hand part of the tail. Okay? Naturally, it can't match the bimodality of this Gaussian mixture, but again, you can see the way that it's doing a pretty decent job of approximating within the log concave class. But maybe one of the main questions we might ask is, what if we have an empirical distribution of some data and we want to do non-parametric density estimation without choosing any tuning parameters? Okay? So here's a few pictures of what the log-concave maximum likelihood estimator looks like. This was an example where I drew 1,000 observations from a standard bivariate Gaussian density. And what you can see, maybe from this top left plot, is that there's a very small discontinuity on the boundary of the convex hull of the data. So the density estimate is supported on the convex hull of the data. In fact, on the log scale, so this plot on the top right here is showing that the estimator you get is obtained as a minimum of a bunch of affine functions. Okay? And another way to see that is by looking at this sort of cartoon on the bottom. So in 2 dimensions, the logarithm of the log-concave MLE is what I'd call a tent function. So what I mean by that is to each of the data points, you associate a tent pole, which is coming up in the 3rd dimension. And then for a certain vector of tent pole height, the logarithm of the MLE is what you get by stretching a taut tent over these tent poles. Okay? So really what I've done is I've reduced my infinite dimensional optimization problem over the class of all log-concave densities or upper semi-continuous log-concave densities down to a finite dimensional one. That is over the class of tent functions, right? But it's still an n-dimensional one. I've got one tent pole for each of my observations. N could be large, and so this is definitely not a trivial computational problem. I can rewrite it as a convex optimization problem, but it's a non-smooth convex optimization problem. I've done quite a lot of work on algorithms for computing the log-concave MLE. There are very fast algorithms, not due to me, that work in 1 dimension, and it gets slower as you go into high dimensions. Certainly 2, 3, maybe 4 dimensions, if you're prepared to hang around for a while, is doable, but not so much when you get into higher dimensions. Okay, now we might ask, well, what can we say about the performance or the properties of this log-concave maximum likelihood estimator? So here is a result I'll call a basic inequality because it comes from the first order stationarity conditions of the optimization problem. So I'm going to compare my original distribution P in this class curly PD with the log-concave projection distribution, which I'll call P star. Okay, so it's interesting to compare these 2 distributions. And this basic inequality is stated in terms of a certain perturbation function, delta. It says that if delta is such that this log of the psi star p plus t times this delta is concave for some sufficiently small t, positive, then I have an inequality between integrals of delta with respect to p compared with integrals of delta with respect to p star. Okay? So that looks a little bit complicated and hard to understand, but certainly one case I can understand is I'm allowed to take delta to be a concave function here because the logarithm psi star is a concave function, so if I add t times delta and delta is concave, that's still going to be a concave function. So that's an allowable choice. And when I do that, this tells me that there's actually a convex ordering between the log-concave projection distribution P star and the original distribution P. Okay, what do I mean by that? That says that the expectations of convex functions under P star are bounded above by expectations of convex functions under P. Right? As a special case, specializing further, if I take H to be an arbitrary linear function, I see that the P star has got the same mean as P. So if I go back to this distribution, this density plot here, when I was doing this from an empirical distribution of some data, what I'm saying is that the mean of this fitted log-concave maximum likelihood estimator is exactly the sample mean. Not is converging to the sample mean, but is exactly the sample mean. Okay? On the other hand, actually, there'll be a strict inequality, for instance, if H were a quadratic function. So you'll be shrinking the variance here, or the covariance. And actually, we'll be able to exploit that later on in the talk. Okay, another very natural question is, so in what sense do I need to be close to a distribution P for the corresponding log concave projections to be close? So in other words, I'm asking about the continuity properties of this psi star map. And the first result in this direction, again, dates back sort of 15 years or so, and relates to the notion of Wasserstein distance. So I think probably many people, but probably by no means everyone, will be familiar with the Wasserstein distance. One can measure this in different metrics. Here I'm thinking about an L1 Wasserstein distance. I'm looking at an infimum over all couplings of random vectors x and y, where x has distribution p and y has distribution q of the expected value of the Euclidean norm of x minus y. That is a notion of distance between distributions. For instance, in the univariate case, I could think of this as the area between the corresponding distribution functions. So the result says that this map, psi star, if I think of it as a map from curly PD, but now metrized by the Wasserstein distance to the space curly FD, but metrized with the total variation distance, that's a continuous map. Okay, so that's answering, at least to some extent, my question about continuity. Unfortunately, however, it's not uniformly continuous. So why is it not uniformly continuous? Well, if you remember, in our class curly PD, we had to rule out this case where our distribution was supported on a hyperplane. And that gives you a hint somehow that if I were getting closer and closer to a hyperplane, then things might be looking bad for me in some way. And in particular, if I took Pn, for instance, to be a uniform distribution on the interval minus 1 over n to 1 over n, and I took Qn to be a uniform distribution on the interval from minus 1 over n squared to 1 over n squared, then certainly the Wasserstein distance between those two distributions would be tending to 0, but those would be log concave distributions, so the log concave projection would agree with the original densities, and the total variation distance between those densities is not tending to 0. Okay? So that then you can see that this is not uniformly continuous. This is a little bit annoying. In particular, it doesn't say anything about the sort of rates of convergence that you can hope to get from the log concave projection, because it's not quantitative. So for 10 years, I was sort of struggling for a more quantitative result, and 10 years and one very clever collaborator later, I was able to answer this question. So this is a result with Rina Feugl-Barber from the University of Chicago. So it's a little bit technical, but I think it's something that we can understand. So for distributions P in this class curly PD, I'll write epsilon P for what you can think of as something like a robust version of a minimum eigenvalue of the covariance matrix of an observation from P. It's not exactly that, because in curly PD I don't necessarily have a finite second moment, so this is more related to the first moment. And I'm thinking about projections into univariate directions, and I'm taking a kind of infimum of the expected value. So I'm sort of looking at how concentrated I am in each direction, and I'm looking at the worst case over all unit directions I could choose. So first of all, if I'm in curly PD, the epsilon P is positive. Well, it's clearly positive for each fixed U, but actually it's not too difficult to show that even when you take an infimum over U, it's still positive. And what we're seeing is that now the Hellinger distance, so this defines the same topology as the total variation distance, but it's a slightly larger distance. The Hellinger distance between the log concave projection of P and the log concave projection of Q is bounded above by the Wasserstein distance between P and Q to the power of a quarter, and then divided by the maximum of these, this epsilon P and epsilon Q in the bottom, again to the power of a quarter. So this is kind of interesting, because I'm getting a bound between log concave projections in terms of something that doesn't depend upon the log concave projections at all. It's just about distance between the underlying distributions. So for instance, I could take Q to be a distribution P and P to be an empirical distribution, and what I'm able to get here is rates of convergence for the log concave projection, or the log concave maximum likelihood estimator, to at least the log concave projection of the true distribution. And that would be in terms of the Wasserstein distance between the empirical distribution and the truth. Unfortunately, at that point, I can rely on another very beautiful result due to Jing at the front of the audience here on the L1 Wasserstein distance between an empirical distribution and the truth. And Jing will tell me that the rate of convergence I get here when I plug in this bound, at least in one dimension, would be 1 over n to the half minus 1 over 2q, where q is the number of moments that you have for the distribution. I think that's right, isn't it, Jing? Yeah. So you can regard this result as saying that the log concave projection is locally Holder 1/4 continuous. So here's the 1/4 power appearing here. Turns out that this 1/4 is optimal. You couldn't have a faster rate here. And the local fact is coming from the fact that we've got this epsilon p, epsilon q, the maximum of these in the denominator. And so that would be blowing up as we approach the boundary of this curly PD space. Okay, so that's a kind of worst case over all distributions. But what if I specialize to the well-specified case where my distribution actually has a log concave density? So this was a result that I was able to prove with Arlene Kim, who's also in the audience here. And it's a minimax lower bound that tells me about, that gives a kind of lower bound or a benchmark against which no estimator could do better. Okay? So the result says that if I look at the worst case risk, and I'm measuring risk in terms of the squared Hellinger distance here, and then I take an infimum over all estimators, then a lower bound for this is given by something of order n to the minus 4/5 in one dimension, and n to the minus 2 over d plus 1 when the dimension's at least 2. Okay? So this result came as a very big surprise to me, certainly, but I think also to the rest of the field. In particular, this 2 over d plus 1 exponent is not so familiar within nonparametric statistics. I would have expected the answer to be 4 over d plus 4 here. So why would have I expected that? Well, any concave function is twice differentiable almost everywhere. And if you are twice differentiable, then your concave, if and only if your Hessian matrix is negative definite or non-positive definite. So essentially, concavity is like a second derivative condition, and you would expect to get the same rates of convergence as if you had something like two bounded derivatives or belong to a Holder class of smoothness 2. And what we're seeing is that intuition is correct in one dimension. It's also actually correct in 2 dimensions because 2 over 2 plus 1 is equal to 4 over 2 plus 4. But in 3 or more dimensions, you're actually getting a slower rate of convergence. And what's really going wrong here is it's sets of measure 0 that are coming back to bite you. I said that concave functions are twice differentiable almost everywhere, and it's the almost everywhere that's hurting you. Because, for instance, these densities can be badly behaved, in particular discontinuous, on the boundary of their support. Uniform densities on convex compact sets are log concave, right? They have a discontinuity on the boundary of their support. And it's actually the difficulty of estimating the support of the density that's driving this minimax lower bound in 3 or more dimensions, not estimating the bulk of the density here. Okay, so no estimator can do better than this rate in the worst case. Yeah, okay, so the constant can actually be chosen independent of d, it turns out. So then we might ask, well, what about this log concave maximum likelihood estimator, which seemed like a nice estimator to study? How can we quantify its performance? Well, I'm actually going to make my life a little bit harder for myself now, and I'm going to work with a larger notion of distance than I worked with for the lower bound. Of course, if I can match the upper and the lower bound when I'm even working with a larger notion of distance for the upper bound, then that's a stronger result. And the result, the loss I'm going to work with is what I call the dx squared. It's like a Kullback-Leibler divergence in that it's looking at a log ratio of the estimate to the truth, but it's taking an average with respect to the empirical distribution rather than with respect to the Fn hat, which would be the ordinary Kullback-Leibler divergence. But it's a very standard fact that the squared Hellinger distance is bounded above by Kullback-Leibler divergence. What's very particular to the log concave maximum likelihood estimator, and what you can actually prove from that basic inequality that I introduced earlier, is that this Kullback-Leibler divergence is bounded above by this dx squared distance, or divergence. It's not a distance. So the theorem on the upper bound side, again from my paper with Arlene from 2016, studies the cases d is 1, 2, and 3. So it says that we get this risk of order n to the minus 4/5 when d is 1. That exactly matches what we saw in the minimax lower bound. And when d is 2 and d is 3, it exactly matches, apart from this rather irritating log n term. Okay, but still, I was sort of trying to manage expectations when I talked about the Grenander estimator being within a factor of 10 is good. Still being within a log n factor is still pretty good with us, and we were kind of happy with this. So these rates are getting quite slow quite fast. I mean, n to the minus 2 over d plus 1 is already indicating that this is not a method that you could use for high-dimensional data. You need some further structure to make some more progress, and that is something that I've thought about in different contexts I won't talk about today. But nevertheless, this result was extended in 2019, going from a dx squared distance back to the smaller squared Hellinger distance, but we get the same bound of order n to the minus 2 over d plus 1 up to this logarithmic factor, even for dimensions greater than or equal to 4. Interestingly, that the argument is completely different and wouldn't work for 1, 2, and 3 dimensions here. So it's kind of nice that we were able to, between us, get everything resolved here. Okay, so that story all was about the kind of worst case. We take a subprimum over all log concave densities. Remember when we thought about the Grenander estimator, we had to restrict this class to this curly GHL set. What's nice about the log concave density estimation setting is that we don't need to sort of compactify the class by making further restrictions. You can take the sup over the whole class, and that's kind of nice, I think. But there are complementary questions one can ask about, are there any densities that you can hope to estimate faster? The spoiler is that I wouldn't have asked the question if the answer was no. And so how could we think about that? Well, remember that the tent function form of the log concave MLE, this maybe hints at the fact that if the truth came from, was of this tent function form on the log scale, perhaps with not too many affine pieces, then you might hope to do particularly well in terms of estimating it. Okay? So the simplest situation you might think of is where you have a uniform density to estimate. Okay? And a very simple result that I like here says that the risk measured now in total variation distance of the log concave MLE is bounded above by 4 over n to the half. So this is getting a parametric rate of convergence with no log factor, but it wasn't like I told the estimator the density was uniform. It's just that the density is automatically adapting to this property. I find this a very kind of elegant property that's sometimes available to non-parametric procedures, in particular quite often available to shape constraint procedures, and a great attraction of this field. Of course, uniform densities are a slightly somewhat restricted class. So how can we push this further? Well, I'm going to introduce the class of what I call log k affine densities. So that is the univariate version of a tent function on the log scale. It just means that there's a finite collection of intervals which partition the support, and where the logarithm of the density is affine on each of these intervals. Okay? So a result from a paper with Arlene and Aditya Kuntapaina says, it gives what I'll call a sharp oracle inequality. So we're assuming that the truth is a univariate log concave density, and I'm getting a bound on this dx squared distance in expectation. To try to understand this bound, let's first suppose that the F0 does belong to this log k affine subclass. So it's got k affine pieces. In that case, this second term, this what you might call an approximation error term, can be taken to be 0. So I only need to worry about this term here, and what we're seeing, if we can just glaze our eyes over this logarithmic factor, is that we're getting this k over n rate of convergence. So essentially a parametric rate of convergence. This is as fast as I could do if you told me in advance that the density was of this log k affine form, and you told me the partition. Okay, so that would be really good news, and we're adapting to that up to this logarithmic factor. More generally, I don't have to belong to this log k affine subclass. In that case, I incur an approximation error term measured in terms of Kullback-Leibler divergence, and I call it a sharp oracle inequality because the leading constant of this approximation error term is 1. That's the best I could hope for here. And then I'm allowed to take a minimum over all values of k, so I can trade off the estimation error against the approximation error here. So that says that there are subclasses of densities that I can adapt to at almost a parametric rate. And there are generalizations of these results to multivariate cases as well. And that's another thing that I've worked on. It gets more complicated, and I won't go into them here. Let me talk about one or two methodological extensions. You might think to yourself, when you look at that density estimate, well, it's not so smooth. It's got these ridges, and it's supported on the convex hull of the data. Maybe I could get a smooth version, but then you think to yourself, but then I've got to choose how much I've got to smooth, and then I'm back to this problem that I had with kernel density estimators. But there's a nice way around this. So I can take my log concave MLE, and I can convolve it with a Gaussian density whose mean is 0, and his covariance matrix is what I'll call A hat. And A hat here is the difference between the sample covariance matrix and the covariance matrix of the log concave MLE. Now, it's not a priori obvious that this would be a non-negative definite matrix, so I could use it as a covariance matrix. But in fact, it is the case because of that convex ordering property that we saw, right? That we shrink the second moment in constructing the log concave MLE. That tells me that this A hat is actually a positive definite matrix, so I can use it. Of course, convolutions of log concave densities are log concave, so I'm staying within the log concave class, and now I've smoothed the estimate in a nice way. The reason why this A hat is a very natural and sort of still fully automatic choice is because now I'm matching the first 2 moments of the data. When I convolve with a centered Gaussian, I don't change the mean, so the mean still agrees with the sample mean, but now the overall covariance matrix is the covariance matrix of the Fn hat plus the covariance matrix, in other words, the A hat, and they add up to give me back the sample covariance matrix. Okay? So here is what the smooth log concave MLE looks like. We've got in red, we've got the original log concave MLE, and in green, we've got the smooth version, and it's just smoothing out the rough edges, as it were, a little bit. If you look very closely, I think you could make a case that the smoothed estimator is closer to the original log concave MLE than either of them is to the truth. I don't have a really strong result in that direction, and I'd be very interested in one. This is what you get on the log scale here. Okay, in another direction, maybe there are some people here who have an interest in information theory. So a really fundamental quantity in information theory is the entropy, and here I'm thinking about the differential entropy or Shannon entropy of a density f. So that's a quantity I'll call h of f, defined to be minus the integral of f log f. Information theorists are very interested in entropy, and in particular in entropy maximizing distributions. So for instance, Gaussian densities maximize entropy subject to a variance constraint, so subject to having variance less than or equal to sigma squared. The density that maximizes entropy is Gaussian. On the non-negative half-line, the density that maximizes the entropy subject to a mean constraint is the exponential density. So there are many common densities that maximize entropy subject to different sorts of constraint. And I want to ask the question, if I give you a distribution in the class curly PD, how do I maximize entropy subject to now a different sort of constraint, subject to a convex ordering constraint? So I'm being a little bit sloppy with my notation here. I've got a density on the left of the convex ordering inequality and a distribution on the right, but hopefully it's clear what I mean. I mean the corresponding distributions are convex ordered. Okay? want to maximize entropy subject to this convex ordering constraint. All I'm imposing is convex ordering, and the answer is that it's a log concave projection of P, right? So my flabber was gasted when I discovered this, right? I'm not imposing log concavity in any way here. It's just falling out of this convex ordering property, which I find really nice. And another reason that I really like this area of nonparametric inference under shape constraints is because you form connections with all sorts of different areas, and here with information theory. I have a confession, which is that I don't have an immediate application for this result. I just like it. Okay, so to finish up the first part of this talk, I want to list a few open problems. I know I promised to do this, and there'll be some early career researchers in the audience, and people who supervise early career researchers, people who want open problems. So I've listed 4. The first of them is a computational problem, and then I have 3 theoretical questions that I think are interesting. Okay, so the computational question, so I actually still think that there's scope for faster algorithms for computing the log concave MLE in a multidimensional case. But I think a variant of this problem that would be particularly interesting would be, can I do better than just starting from scratch again if you delete one observation, or you give me one new observation? Right? At the moment, I've got nothing better that I can do than start from scratch in terms of optimization. It would be really nice if there were quick updates available here. Okay, I introduced the smooth log concave maximum likelihood estimator. I should say that in the one-dimensional case, that was originally proposed in a very nice paper by Lutz Dumgen and Dominik Röfebach. But in terms of the theoretical properties, we know about it matching the first 2 moments of the data and things, but in terms of how close it is to the truth, we don't have too many ideas at the moment. What can we say about the boundary behavior of the log concave MLE? Shape-constrained estimators often exhibit kind of unusual behavior near the boundary of their support. So let me give you one sense in which that would be true here. If I had data from a uniform distribution on the interval 0, 1, and I look at the log concave MLE at the minimum order statistic. So ideally, I'd want that to be converging in probability to 1, okay? But that's not going to be the case. In fact, I suspect it converges to a non-degenerate distribution supported on an interval from, let's say, A to 1, and I'd be very interested to know if A is equal to 0 in that problem. But more generally, I think it's of interest to study these boundary behavior properties. How far in would I have to come from this minimum order statistic before I can guarantee that I am kind of being consistent in this uniform case or more complicated cases? Here's another kind of question. What about if I'm in a multivariate case and I've got some missing components in my data? So the simplest situation here would be, I've got, say, bivariate observations. Let's say the missingness is the simplest form of missingness, MCAR missingness, missing completely at random. So the data generating mechanism and the missingness mechanism are independent. Can I exploit the observations for which I only see one coordinate to do better than just throwing those observations away? You know, in the kind of ideal situation or a kind of limiting situation, I'd have so many observations with one missing component that I could think of the marginal densities as being known here. Does that help me in terms of estimating the log concave density, the bivariate log concave density? Okay, so those are a few open problems, and that's the end of the first part of this talk. So maybe I'll just pause for a moment and ask if there are any questions at this point. Shuhong. Yeah. So you're asking, you want me to answer my own questions, my own open problems? No, I don't. Yeah, Ed.
So the log, if I get it right, the log affine class contains the uniform.
Yeah.
But you get much faster convergence for the uniform. So it must be the case that as you get closer, you get rapidly faster convergence.
as I get closer to a uniform. Yeah, certainly. So, the two forms of the result here, this TV is a smaller notion of distance than the dx squared, and in this smaller notion, I don't have any log penalty here. Yeah, there was a switch that I maybe didn't emphasize too much there. Yeah. Yeah, Boaz.
So what about pictures of log concave densities?
Okay, so algorithmically, there's something I played around with about 15 years ago here. And the natural thing to do is to think about a kind of log concave EM algorithm as a way of fitting log concave mixtures. So that means that you need to compute a log concave MLE at each iteration, so it's going to be a little bit slow, but certainly in one dimension and maybe in two dimensions, that's potentially still doable. The EM updates are doable. But one thing I found, and I didn't pursue this too far, I probably should have done, is okay, first of all, you can run into this issue where you can have like a Dirac catastrophe again, because one of the components can concentrate on one observation, the other one covers the rest of the support, so you can run into this sort of likelihood blow-up situation. Exactly. You also have this if you don't restrict the variance in a mixture of Gaussians. But the support is the whole of the data, so if these are relatively well-separated components, then this left-hand component is going to be very, very negative on the log scale in the right-hand component. And then you kind of need a way of saying, well, I don't want to have it supported there, so I'll kind of truncate the support, and it gets a little bit messy. And I didn't pursue it too much further. But I think in principle that's doable. Yeah. Okay, let me move on and talk about the second part of the talk. So the kind of core problems of density estimation and regression in nonparametric inference under shape constraints have received a lot of attention over the last 15 years. And fortunately now I think we have some pretty good results for a lot of different sorts of shape constraint models. And what I've found in the last few years is that people are starting to absorb these techniques and ideas into other more involved statistical problems. So I've done some work, for instance, on subgroup selection with shape constraints, on conditional independence testing with shape constraints. I was going to talk a little bit about those two problems, but I think it would have just been too much for one talk. I'm instead going to focus on a third problem that I thought about that incorporates a lot of shape constraints, and that's linear regression. So hopefully we're going to be back on material that should be really very familiar to people. I should have just wrapped up with what I was saying on the first part of the talk. I think everything that I've said here should be fairly clear, so I think I'll just move on. So this second part of the talk is all work that I've done with three fantastic collaborators. Oliver Feng, who was my PhD student and postdoc, is now at the University of Bath, but he's moving very, very soon to LSE. Min Xu is at Rutgers University. He's the brains and the brawn behind the ICSDS conferences, and Yuchun was Min's PhD student, and he's now in the industry. Okay, so linear regression. Everyone thinks they know how to do linear regression, but let's say I didn't know how to do linear regression. Then I would turn to my friend Jing, and I would say, Jing, how should we do linear regression? To which Jing would reply, he would indeed reply, use ordinary least squares, okay? But what if I were to say, why is this the best you can do? Jing would say, okay, by the Gauss-Markov theorem, okay? All right, so the kind of takeaway message from this part of the talk is I think statisticians tend to rather over-interpret the Gauss-Markov theorem. We tend to think it means that ordinary least squares is optimal even when we don't have Gaussian errors. And I want to argue here that that's not quite true, because we're only comparing against linear unbiased estimators in the Gauss-Markov theorem, and that if we allow ourselves to consider biased and nonlinear estimators, then we can potentially do much better in situations where our error distributions are at least appreciably non-Gaussian. So the setting I want to consider is one where I have IID covariates that are going to be independent of our errors, and the errors are going to be IID also with a density that's F0, and we have this linear model here. And the sorts of biased nonlinear estimators that I want to think about are M estimators. So if you're not familiar with M estimators, if you're given a differentiable loss function, curly L, I should say this is not the same loss function as in a decision theoretic sense. This is a loss function that's going into an algorithm. Then I can define an M estimator as the empirical risk minimizer with respect to this loss function curly L. And given that L is differentiable, any minimizer must be a stationary point of this optimization problem, so it must be what I'll call a Z estimator. It must satisfy these Z estimating equations. And examples of loss functions that I might be interested in here, well, of course, there's the least squared loss, which is plotted in the dotted line here, but that might be rather vulnerable to outliers or heavy-tailed error densities. And so I might work with this L1 loss, this dot dash line, or I could interpolate between them with this famous Huber loss function, which is quadratic around the origin between minus k and k, and is linear thereafter. Okay? Of course, you have to choose the k. You have to choose this transition point between the quadratic and linear behavior. So I'm going to restrict my attention to loss functions, or equivalently the negative derivatives psi, that are what I call Fisher consistent. That's saying the expected value of x1 times psi of x1 is 0, psi of epsilon 1 is 0. I'm assuming x1 and epsilon 1 are independent, so I could factorize that expectation out here. And that's saying that the beta 0 satisfies the population analog of these Z estimating equations. Okay? All right, so we actually know about the asymptotics of M estimators. This is well understood. You could look in, for instance, Art van der Waart's book. And so it turns out that under some mild regularity conditions that I don't want to particularly focus on here, this M estimator would be root-n consistent. It would be centered around 0 asymptotically. But what I'm particularly interested in is the form of the covariance matrix here. So there's this expectation of x1, x1 transpose inverse. That's a matrix here. There's not much I can do about that. I'm sort of given my covariates. But what I'm particularly interested in is this term in green, which is a scalar quantity. I might call it the asymptotic variance factor, because this depends upon the psi function, right? So this is something that I get to choose, and I might choose it to try to make the asymptotic variance of my M estimator as small as possible. So to set us back in a context we're very familiar with, if I take my loss function to be the squared error loss, or if I divide that by 2, which makes no difference, then psi of z is minus z, and the asymptotic variance factor is just the second moment of the errors. So that would be a formula that I hope will be familiar to people from courses on linear regression. So the question I want to think about to start with is what would be the optimal choice of loss function? What's the optimal choice of L, or equivalently psi? Okay? And I want to think about this in a context where F0, this error density, is absolutely continuous, and I'll write psi 0 for its score function. This score function is the derivative of the log density, so the derivative of the density divided by the density, I think of 0 over 0 is 0 here, and with a finite Fisher information. Okay, we also know how to answer this question. So if I take my curly L to be minus the log of F0, this amounts to doing maximum likelihood estimation, right? Then my psi, which is my minus the derivative of the L, is equal to the psi 0, the true score function, and then we have this famous formula for the asymptotic distribution of the maximum likelihood estimator, and the important term here is this asymptotic variance factor, which is 1 over the Fisher information. Okay? And we know from the Cramér lower bound that this is the best that I can hope for. Again, there are regularity conditions I don't want to focus on. Well, that sounds like we've solved this problem, so why are you thinking about this, Richard? Well, there are a couple of issues. The first is, you notice that I chose the L to be minus the log of F0, but nobody tells me what F0 is here, okay? So that's going to be one issue. But the other is a computational issue. So this is what I get when I try to fit a Cauchy log likelihood to some data. And you can see that you get this highly multimodal, cuspy likelihood surface, which could be very difficult to optimize. Right? So for that reason, what I'm going to do is I'm going to restrict my attention to what I'll call convex M estimators. And a convex M estimator is just one for which this L function is convex, or equivalently, the psi function, the negative derivative of L, is what I'll call antitonic. So for the purpose of this talk, being antitonic doesn't mean that you're some kind of gin addict. It just means that you're decreasing. It is the opposite of being isotonic. Okay? So in that case, your oracle maximum likelihood estimator, where you took L to be minus the log of F0, would be a convex M estimator if and only if the error density is log concave. We see log concavities making a reappearance again. Okay? But actually, I'm going to be particularly interested in the case where the error density is not log concave, and I'm going to ask the question, what price am I going to pay for the computational convenience of working with this convex M estimator? Okay? Because one of the great attractions of convexity is that any local minimizer is then automatically a global minimizer. And it's very straightforward to compute these convex M estimators. So here's what I'm going to try and do. I'm going to write psi down arrow for the convex cone of decreasing right continuous functions with this finite Fisher information. And I'm going to try to choose this psi amongst this class of decreasing score functions that minimizes the asymptotic variance factor. And that's on the population level. And having done that, I'm going to go back to having some data. And I'm going to think about trying to construct a data-driven choice of convex loss function, which I can then minimize to give me a convex M estimator, and hopefully does as well as I can within the class of all convex M estimators. Okay, so how can we hope to minimize the asymptotic variance? So given a distribution P0 with a uniformly continuous density F0, I'll write S0 for its convex support. And then I've slightly changed the definition, in fact, generalized the definition of this asymptotic variance factor because I don't necessarily want to assume I'm absolutely continuous. I've got now the integral of psi squared times F0 divided by this Lebesgue-Stilches integral, but that directly generalizes what I had before. It's the right form of generalization. And my goal is to minimize this asymptotic variance factor over all decreasing functions psi. And the first thing you might observe is that if I multiply a given psi by a scalar factor little a, then I multiply both the numerator and the denominator by a squared, and that cancels out. Okay? So that might give me the hint that the way I might try to minimize this would be to fix the value of the denominator, for instance, to be 1, and then try to minimize the numerator. Or equivalently, I might think about writing down a Lagrangian. Okay? Actually, I'm going to write down a Lagrangian with the outer Lagrange multiplier. And it's what I'll call a score matching objective. So the reason for this terminology will become apparent later, but let me mention that score matching is becoming an extremely hot topic in modern machine learning and statistics. Anyone who was in Yiting's superb talk earlier this morning will know that they're forming the heart of diffusion models and generative modeling. It's really, there's a sort of explosion of interest in this area at the moment. But for now, this is just an objective function that we're going to try and write down. What's the connection with my original problem? Well, notice that minimizing v is the same as minimizing minus 1 over v, and this is the expression for minus 1 over v. And now I can see this as the minimum value of a quadratic in C. Okay, so I could just find this by completing the square in this quadratic in C, and I will get back exactly the expression on the left. But this guy is my score matching objective evaluated at C times psi. So what have I learned? I've learned that minimizing this asymptotic variance factor over this convex cone is equivalent to minimizing this score matching objective up to a scalar multiple. Okay, how's that helped me? It's helped me because the score matching objective is convex, which the original objective wasn't. Okay, that's kind of nice. So now I explain where this notion of score matching or score projection comes from, and it comes from an integration by parts formula. So if I just integrate the second term that I had in the score matching objective by parts, at least in the absolutely continuous case, then I get this expression here, and I can rewrite that as a squared L2 difference between the psi function and the psi 0 minus the Fisher information, but the Fisher information doesn't depend on the psi. So minimizing this the score matching objective is equivalent to minimizing this squared L2 difference between the scores. Okay, and that's why this is called score matching. So I can think of this as trying to compute the best approximation to this score function within this decreasing class, and by best I mean best in an L2 P0 sense. And I'll call this psi 0 star, the optimizer, the antitonic score projection of the original psi 0. I want to tell you how to compute psi 0. Before I do that, I'll just introduce the notion of antitonic information. So remember we had this notion of Fisher information, which I could write down as the integral of the square of the score function with respect to the density F0, and that minimizes, so the reciprocal of the Fisher information is the minimum value of this asymptotic variance factor over a large class of test functions, for instance those that have a continuous derivative and compact support. Analogously, I can define a notion of antitonic information where instead of integrating the psi 0 squared, I'm integrating the psi 0 star squared with respect to F0. And analogously, 1 over this antitonic information is the minimum value of the asymptotic variance factor over a restricted set, this convex cone of decreasing score functions. So then it's very natural to think about an asymptotic relative efficiency, that the ratio of these, the antitonic information to the Fisher information, and that quantity is necessarily bounded above by 1 with equality if and only if you're log concave. Okay, now I want to explain how we solve this score matching problem. I'll do it in the context of an example, but this is actually the general solution. The example I'll think of is a Cauchy density. The Cauchy is definitely not a log concave density because its tails are far too heavy, right? Polynomial tails. A very nice result due to Bobkov says that if I think about the density quantile function of the Cauchy density, I should explain what that is. Okay, we've got a Cauchy density, we've got its distribution function. The density quantile function is the composition of the density function with the quantile function. That's got quite a simple form in this case, and it's plotted in green here. The Bobkov result says that the density quantile function is concave if and only if the original density is log concave. Well, the Cauchy is not log concave, and therefore the green is not a concave function. But I can compute its least concave majorant. Okay, we saw this quantity appearing in the Grenander estimator, and it's making a reappearance here as the blue function. So I've got this density quantile function, I've got its least concave majorant, and now I compute its right derivative. So we're coming back, again, similar sort of operations to what we did with the Grenander estimator. When I take this right derivative of this concave function, I'm going to get a decreasing function. In fact, in this case, because it's affine, then follows the truth, and then is affine, the derivative is going to be constant. Then it's got actually a rather simple formula, and then it's going to be constant. Okay. On the score function scale, the Cauchy score function's got a very simple formula. It's just minus 2z over 1 plus z squared. That's in green here. Of course, that's not decreasing because the original density is not log concave. But the blue is the decreasing approximation, and I claim that this is the best decreasing approximation that I can get to the green within this class in this L2P0 sense. So then I just compose this with the original distribution function to get myself back on the original scale. And that gives me the projected score function. So more generally, the theorem says that if I use this algorithm, so I take the least concave majorant of the density quantile function, I take its right derivative and I compose it with the distribution function. That is a right continuous and decreasing function, and moreover, interestingly, it automatically satisfies this Fisher consistency condition, so I don't need to impose that separately. And moreover, this is the unique minimizer of the score matching objective, and it minimizes also this asymptotic variance factor. So this is the solution to the problem of how I should choose my psi if I want to minimize the asymptotic variance of the resulting M estimator in linear regression. So if I go back to the loss function scale, the Cauchy loss is not a convex loss, and I'm approximating it by this loss in blue here. And the first notable thing here is that in the tails, this is growing linearly. Right? This is like the Huber loss function, or the least absolute deviation loss. And that's very attractive when I've got a heavy-tailed density like the Cauchy, because this is kind of minimizing the impact that the outliers are going to have. In fact, what we can prove, if I focus on the right tail for simplicity, is that the loss function, this projected loss function, will grow linearly in the tails if and only if the hazard function of the original density is bounded. So bounded hazard functions correspond to relatively heavy-tailed densities. So an exponential density would have a constant hazard function, for instance. And that's exactly when you want to have the impact of the outliers not being too great. And what we're seeing is that this optimal loss function does look rather Huber-like. It's not actually a Huber loss function because it's got this logarithmic behavior near the origin. But if I were to Taylor expand this logarithm, then the dominant term would be a quadratic term, and then we're getting this linear growth in the tails. So I can then compute the antitonic information and this asymptotic relative efficiency, and what we find, which I again found pretty remarkable, is that even though the Cauchy density is way from being log concave, the loss in the statistical efficiency I get is really quite small. I get more than 87% efficiency here, okay? And so the kind of argument is that the loss of statistical efficiency that you incur may be small relative to the computational convenience of working with this convex loss function. Okay, so I can think about this projection in a different way. I've thought about it in terms of the score functions, but I could also think about it in terms of the original density functions, and that the Fisher divergence between two densities is defined as this squared L2 distance between the corresponding score functions. And the proposition says that there is another notion of projection onto the class of log concave densities via this psi 0 star, the right derivative of the log of this f0 star. And there's another information theoretic inequality that I again like but have no application for, which says that the Fisher information of the projected density is bounded above by the antitonic information of the original density. It's kind of interesting fact. But overall, this gives me another notion of projection onto the class of log concave densities. I'll call this the Fisher divergence projection. Okay? So now, in the first part of the talk, we saw a Kullback-Leibler or maximum likelihood notion of projection. Here we're seeing a Fisher divergence projection. That gives us, in principle, two competing methods for estimating my vector of regression coefficients, according to which projection I choose to use. And even though I argued in the first part of the talk that the maximum likelihood estimator was great as a density estimator, what I'm seeing here is that the maximum likelihood estimation projection in terms of the estimate of the vector of regression coefficients can be arbitrarily inefficient relative to the Fisher divergence projection, even when you're really quite close to being log concave, in the sense that this asymptotic relative efficiency is bigger than 1 minus epsilon. That, again, I found kind of surprising. And basically, I guess the moral of the story is choose your projection to suit the problem at hand. For the problem of linear regression, you definitely want to be doing Fisher divergence projection and not log concave maximum likelihood estimation. So that was all on the population level. I'm going to get bitten to death by a mosquito here. I want to now return to having some data and my random design linear model. And I want to think about a situation where either my underlying density F0 is symmetric or I've got an explicit intercept term in my model. And the basic strategy I want to employ for doing linear regression is not just to use ordinary least squares, sorry, Jing, but is to do a sort of adaptive convex M estimator. So the high-level idea is that I start with a pilot estimator of my vector of regression coefficients, I compute residuals, and then I obtain an estimate of the antitonic score projection based on these residuals by antitonic score matching. That gives me a psi hat. I can compute its negative antiderivative to give me a loss function, a data-driven loss function, L hat, and then I can do just ordinary M estimation with this convex loss to compute an update of the beta hat. Okay? So that all sounds good. There's a snag, though, and the snag is that this score matching fails when done in a naive way. And the reason it fails is because on the empirical scale, this is my score matching objective, and the trouble is that I can make the derivative here very, very negative at these residuals without paying a price. I just do that very locally, and I don't have to pay a price in terms of this squared error term, and so this score matching objective doesn't have a finite minimum. It's unbounded below. The solution to this snag, at least one solution, is to do smoothing. So we take the residuals and we smooth them to give me a kernel density estimator, call that Fn tilde, and then I plug the Fn tilde into my machine for computing these antitonic score projections. In other words, I just take the density quantile function, compute its least concave majorant, compute its right derivative, and compose it back with the corresponding distribution function. And that's something I can do very quickly because I can use the Parver algorithm. That's a linear time, linear storage algorithm. Okay. So the basic workflow looks something like this in our Cauchy example. The green is the true density of the residuals. This in black is my kernel smoothed version of the residuals. It won't be too surprising to people to see that we've got a negative bias around the peak here. If I compute the density quantile function corresponding to that estimate, I get this thing in black here, and its least concave majorant is in red, which is in some sense estimating the blue, which is the least concave majorant of the true Cauchy density. When I take right derivatives, I get these estimates on the score function scale. So the red is an estimate of the true projection, and then I can take a negative antiderivative to give me these convex loss functions here. Similar ideas can be employed when I have a Gaussian mixture and I get similar sorts of plots. What can I prove about the overall procedure? So let's say I have a sequence of regression models, each indexed by n. Okay, one sort of technical thing I want to do here for the purposes of theory, but not necessarily for methodology, it's not necessary to do this in practice, is that there are kind of three stages to this procedure, which is compute a pilot estimate beta hat, then from your residuals compute this anti-score matching projection, and then compute an empirical risk minimizer. And for theoretical reasons, it's convenient to do this on different folds of the data. So we do a third, and a third. You think to yourself, well, that's going to lose efficiency, but there's this clever idea of cross-fitting, where you just interchange the three folds of the data, and you take the average of the overall beta hats that you get out in the end. This is called cross-fitting. Very nice idea. So for instance, what we end up with in the case of a symmetric density is we have a consistent estimate of the antitonic score projection, and our overall estimate of the vector of regression coefficients is what I could call antitonically efficient. So we can't hope to do as well as the reciprocal of the Fisher information here, but we are doing as well as we could within this convex M estimation class. And there's an analogous result in the case where I have an intercept term in my model. Okay, so I have some simulation results to show, but I always quite like to show something as a demo here to show how this works in practice, show that this is not all just two head in the clouds theory. So we've introduced our ASMR package. That's because of the warm tingly feeling you get when you use it. No, it stands for antitonic score matching. So let's say we have 500 observations in 5 dimensions. I give myself a vector of regression coefficients that looks like this. I generate myself a design matrix, something like this. And then I'm going to generate some observations from a linear model, but with Cauchy errors. Okay, so very heavy-tailed errors. And now what I want to do is to fit this antitonic score matching model, and we've sort of designed the R package to mimic the LM function in R. So just instead of typing LM, you type ASM. We don't have an intercept here, that's why I've got the -1 here. Okay? So that didn't take too long to compute, right? That's the linear time Parva algorithm that's working for us here. And if we type summary, then we can see the estimates and the standard errors that we get from this model. We were trying to estimate what we do, -2, 1, 0, 3, 4, and you can sort of see that the estimates are kind of vaguely close to what they're supposed to be. By contrast, if I were to use this ghastly LM function, no one's heard of this, and I compare the standard errors here, then what are we, about a factor of 15 difference between the standard errors. So that's what we're really gaining by using this antitonic score matching methodology, okay? Well, that was just one simulation, and maybe I tricked R with my randomization seed or something, which I didn't. So let's suppose we look at a larger simulation study. Here we've got 600 observations in 6 dimensions. We're going to look at several different methods, and we're looking at the mean squared error over 200 repetitions. So first of all, I'm going to think about an oracle estimator. This is an oracle convex M estimator. Okay, so this uses knowledge of the error density to give me the optimal convex projection here. Then there are 2 versions of our procedure. So the original ASM is doing what I said, but just one iteration, because what you might do is you might do pilot estimate, antitonic score matching, update, and then you might go back and compute residuals again and update your score estimate and update the beta hat, and you could iterate between those 2 to convergence. That's what we call ASM alt. Obviously that's going to take longer, but it might in principle do better. The LCMLE, this is what I did 15 years ago. That's using the log concave maximum likelihood projection rather than the Fisher divergence projection. I didn't know better back then. The one-step estimator, this is a kind of theoretically efficient estimator, not just antitonically efficient, but efficient estimator. So you could find information about this, again, in, say, Art van der Waart's asymptotic statistics book. And then there are 2, roughly speaking, straw men to look at, one of which is the least absolute deviation estimate, and the other is OLS. Okay? The settings I want to consider, there are 6 different ones. I've got a standard Gaussian density, a standard Cauchy density. I've got a scale mixture of Gaussians, so one component has got a higher variance than the other. I've got a Gaussian location mixture that's got very separated modes to the error density. And then I've got a slightly smoothed uniform density and a slightly smooth centered exponential density. Okay? So of these examples, numbers 1, 5, and 6 are log concave error densities, but 2, 3, and 4 are not log concave. So we've got a variety of different options here. What are we seeing? Well, if your true error density really is Gaussian, the spoiler is that you're not going to do better than OLS. Okay? In fact, OLS is the oracle estimator, which is why these numbers are matching here. But we're not doing too much worse with antitonic score matching. In the Cauchy case, of course, OLS is a complete disaster. And we saw that in the simulation. It's also not doing very well when you've got this heavier component in the scale mixture. In the Gaussian location mixture case, that's a disaster for the least absolute deviation estimator. So many of you'll know that the asymptotic variance there will depend upon on the density at the median of the error distribution. Well, the density at the median is absolutely tiny in this well-separated Gaussian mixture example, and so the variance is very, very large here. But notice the way it also really hurts the one-step estimator and this log concave MLE, whereas by contrast, the ASM is able to cope with this challenging situation really no problem. Least absolute deviation and one-step estimator also struggle with a smooth uniform case and with the smooth exponential density. So really across quite a wide range of simulation settings, these antitonic score matching estimators are doing really a pretty decent job, not very far off the oracle, And there's not too much difference between the one-step estimator and the alternating version. In our package, we actually did 2 iterations to be on the safe side, but 1 would be really fine. Okay, so to wrap up this last part, the main takeaway message I want to leave you with is that I think that despite the Gauss-Markov theorem, I would claim that the success of ordinary least squares is really quite closely tied to having near Gaussian errors. Antitonic score matching, our method, releases you from this Gaussian straitjacket, and it allows you to retain the convenience and stability of working with convex loss functions. One thing I like about this area, and as a kind of template for how shape-constrained ideas can be used in all sorts of other modern statistical problems, is that it's bringing together ideas that are rather classical from robust statistics together with the very modern in terms of score matching, as well as some information theoretic ideas as well. I haven't talked about this, but there's really a kind of big line of work that needs to be done here, some of which have been done, some of which is ongoing, and some which I have in mind to do, which is to kind of incorporate the full toolbox that's available to the LM function to make this something that people will really use. So some things we have already looked at include ideas like getting confidence sets for parameters and doing goodness of fit testing and that sort of thing. But there's certainly more to do here. If you're interested, then the paper on which this part of the talk's been based is this paper here in red, and the R package is called ASM. That's available on CRAN. With that, let me just thank the IMS committee again. I'm really tremendously honored to give this lecture, and I thank you very much indeed for your attention.
Very nice, interesting talk. What happens? I mean, in some practical applications, you have, let's say, inclusive domains, and then there are methods, for example, like many methods, but one of them is the relatively weighted least squares.
Sorry, I couldn't quite catch it.
Relatively weighted least squares, or ILL1 or ILLS, which essentially they just give a weight close to 0 to some of the samples. And I think it would be interesting to see if they perform similarly to your approach, because those entries with very large errors, you may better just neglect them altogether.
Yeah, I mean, I agree that if you've got atoms in the error distribution, we haven't studied that case yet, and that's something we do need to. In fact, that's on my to-do list, but it's not something that I've looked at yet. And I think it will be interesting to see how that's going to affect the estimates. I agree. Ryan.
So around 2013 or 2014, I don't remember exactly when, I think that they were looking at a similar problem, I'm sure you remember, in proportional topology. And I'm just wondering if you can comment on what you see as some differences in high dimensions versus something that's precise like yours in low dimensions.
Yeah, you're absolutely right. Nerdine, and the others that you mentioned did some really nice work. It was one of the things that made proportional asymptotics really a nice setting to study. And everything I've done here is fixed dimension, n going to infinity asymptotics. The main difference is in terms of the characterization of the solution that we get here. There's no such comparable characterization in terms of taking derivatives of least concave majorants of density quantile functions. Your solution is in terms of state evolution equations and things. You could argue that the papers got written in the wrong order. You would expect the fixed dimension one to be done first, but you can be much more explicit about the solution and therefore about the statistical method that you should use than in the proportional asymptotics regime. Yeah.
So have any opinions about whether we would see big qualitative differences. So, for example, one notable result that they had, I think, was that if I have Laplace errors, I'm actually using LAD loss is worse than using least squares loss as soon as the aspect ratio of features to dimension is like bigger than 0.3.
Right.
And I'm just wondering if these are high-dimensional phenomena, or you think that
Yeah, that would be a high-dimensional phenomenon. You know, in a fixed D asymptotics regime, you know that the MLE is going to be asymptotically efficient, and that is the MLE in that setting. So this is definitely a proportional asymptotics phenomenon. Yeah. Yeah, that's a very good question. So not too sensitive, fortunately. Basically, because all I need is a consistent estimate of the anti-sonic score matching objective. So basically, the conditions we need are the bandwidth to tend to 0 with the sample size, and then I've got the derivative of the density divided by the density, so I want to get a good estimate of the derivative. I need n times h cubed to tend to infinity. Right, that's a kind of typical consistency for the derivative, but I don't need to have the precise order in terms of the smoothness of the underlying density or anything like that, because all I'm after is a consistent estimate of the score matching objective. So I have a reasonably wide range of bandwidths that are available to me, and we just use a very naive Silverman's plug-in bandwidth in our implementation. So you've got quite a lot of flexibility there. You mean the computational speed of the algorithm? I think it should be, but I think don't hold me to that. It's pretty quick. Yeah.
Actually, I have a question. I'm curious about the reason of the occasional failure of the one-step method. If you could go back to
Yeah.
the simulation without it here. So to me, the 1s is very close to this ASM one-step, except it doesn't like the shape constraint and also the smoothing step.
Yeah. So I'm actually working on these ideas with one of my postdocs at the moment. It seems that there's a kind of conflict between theory and practice here. That, you know, the title of a paper might be 1 step in theory, 10 steps in practice. It's not that nothing can be done. You can fix this in certain ways, but I mean, definitely these estimators are not used in practice, and it's this sort of failure that means that they're not used. They're just not sufficiently robust. You can see big moves that are getting made when the theory doesn't really describe that adequately.
It added like a regularity of the shape constraint to help the ASM approach compared to one-step.
Yeah, I mean, you've got a convex thing that you're doing here, so you're not going to run into those issues. Yeah.